Okay, so we're going to take a look today at yesterday, or I should say the lesson prior to this one, we looked at strong acids and bases and reviewing kind of the definition of an acid and base. So we are using the Bronsted-Lowry definitions. That's the current theory that is being used. So today we're going to focus on weak acids and bases. So if you recall from the other lesson that strong acids and bases essentially will dissociate or ionize, like they will react to completion or 99% plus. Weak acids and bases are different in that they reach equilibrium, which is why we're talking about it in this unit. So let's look at this in a little bit more in depth. So what happens when a weak acid ionizes? So first of all, strong acids ionize 100%. It is assumed 100%. And a weak acid is essentially less than that. So remember that equilibrium is anywhere between that 1 and 99%. So as long as if it's not 99% plus ionizing, it is considered to be a weak acid. So remember that when we're talking about ionization in water, really what we're doing here is something called a hydrolysis reaction. So meaning our acid is reacting with water. So acids, just to recall, are always the proton or hydrogen ion donor. The base is always the hydrogen ion acceptor. So in this case, we have an acid, and when it reacts with water, water is behaving as a base. So as a result of that, we have our hydronium ion and our conjugate base. Now the difference here between what we saw already and this is now we have an equilibrium. So meaning when those products are produced, you have some of those products reverting back into the reactants. So the forward rate is equal to the reverse rate, exactly the same as when we looked at equilibrium in our last chapter. So here we have an example with carbonic acid. Carbonic acid will donate up hydrogen ion to make hydronium, and our resultant ion is basically bicarbonate or hydrogen carbonate. So here we have our acid, water is our base, our H3O plus is our conjugate acid, and our HCO3 negative 1 is our conjugate base, right? So imagine if this were to go into the reverse reaction, the hydronium would have to donate back, or I should say give away the hydrogen ion back into, so it can become water once again. The HCO3 negative 1 would then become H2CO3. And this is happening continuously. Now, how much does it become product is very similar to when we were looking at equilibrium before. So it depends on the percent reaction. So if I have a 10% reaction, that means I'm going to have 10% product and the remaining is as reactant. So the only difference here is when we're talking about percentage, or I should say a percent reaction, we're now going to refer to it as percent ionization. It's the same thing. We're talking about how much product is made. However, because the process of an acid reacting with a base technically is an ionization of that acid, right? We're creating an ion here. It just has a different name, but the process is like identical, okay? So here's just a visual representation. If you remember the graph in the other PowerPoint, what happened here is you have here is our weak acid. And if this were to be a strong acid, that means that we were going to have 100% products, right? So these two columns would be completed, and you would have barely any green left, right? Less than 1% green. But in this case, here we have only some product produced, and we have a lot of reactant there. So this is an example where perhaps this is only maybe very small percentage of this became product. Maybe this is a 5% ionization reaction, or it definitely looks like it's way below 50%, right? So 50% means you would have half the amount of products, right? So this is an example of And HA, we're just using a generic A, meaning any anion present. So obviously we're dealing with a weak acid here. So obviously the higher the percentage, the more it would favor one side versus the other. So here I would say this is an equilibrium, but it definitely favors the reactant or the reverse reaction in comparison to the forward. So now we're introducing, some quantitative values that we're going to look at here. Because we're dealing with equilibrium, right, we're going to have to start dealing with K again. So if you remember when we first learned about K, we mentioned that K can take on a whole bunch of different scenarios or different equilibrium types. So equilibrium with an acid, our K is called an acid ionization constant, or Ka. So essentially, it's the K value for an acid equilibrium, okay, a weak acid equilibrium. So remember that strong acids do not have an equilibrium, so you'll never deal with K values for strong acids, only weak acids. There has to be an equilibrium to deal with K. So your K expression is exactly the same. So here we have just a typical equilibrium. So here we have our weak acid donating the hydrogen ion to water, making hydronium. And then here we have our anion that's left over after the hydrogen has been removed. So to set up your K expression, it's going to be products over reactants still. Our products in this case are our two ions, hydronium and our anion. And the reactants, you only include the weak acid itself. Remember that liquids are not included in a K expression. So this is showing you products over reactants, but recall that your water is not included. So your Ka expression is products over reactants, but only looking at things that have concentrations. So you would have here your hydronium, your conjugate base, and then of course you have your original weak acid. Okay, so the same thing as with other K values, the larger the K, the more product that is in that equilibrium system. So remember, the higher your numerator value, the higher your K value will be. So if you have a lot of ions that are produced on the product side, you're going to have a very big K. So even though you can have equilibriums, like we mentioned, you can have a variety of strengths, because you might have ones that are 60% product, or you may have things that are 2% product, right? So the strength of your acid essentially is how much ionization is occurring. So the stronger the acid, the more ionization, which means you'll have more products there, and your K value will go up. So if you're ranking, let's say you had to rank 5 or 6 different acids, you can rank them according to strength based on their K values. Okay, at the back of your textbook, you also have an appendix that has a big long list of a whole bunch of different Ka values for different acids. Okay, so here's an example where we have hydrofluoric acid, which is an example of a weak acid. So we have hydrofluoric acid plus water. The hydrogen donates, so we have hydronium and then fluorine ions. So if we were to write our K expression for this, it's hydronium multiplied by fluorine, right? The coefficients are always a 1 when you're dealing with ionization reactions, because remember, we're only moving over one hydrogen here. So we have hydronium and fluorine over hydrogen fluoride, I should say hydrofluoric acid, and notice we're not including water here. So the Ka values are temperature specific, and of course at SATP you have a list of constants in your appendix C9, as I mentioned before. So that's where you would find, hydrofluoric acid, carbonic acid, a whole bunch of different acids there. Now you're going to notice if you look that up, if you look beside a strong acid, the K value will say very large. Okay, it won't even have a number there. It's because if you recall, strong acids 100% ionize. So you essentially have almost all product and very, very, very small amounts of reactants. So the K values are not even worth saying because, first of all, they're not in equilibrium, and they're huge because they're pretty much all product. Okay, so what happens if we have an acid that has more than one hydrogen ion? Okay, so before we get into this, I'll kind of just preempt this to discuss this. So let's say carbonic acid, for example. Technically, carbonic acid has 2 hydrogen ions. Okay, it's important to note that when you are discussing ionizations of acids, only 1 hydrogen moves per ionization. So meaning when carbonic acid loses the first hydrogen, it will become HCO3 -1. Okay, so technically this has 1 more hydrogen. So we can actually have a second equilibrium that's happening here. Let's write the full thing out this time. So if I have our hydrogen carbonate ion, right, polyatomic ion, reacting with water, okay, what happens here is now this hydrogen can be lost to make hydronium yet again, and we're left with CO3 -2. So each equilibrium has its own value. So meaning the K value for, the Ka value for HCO3 is going to be different from the Ka value of this equilibrium because they're going to be different concentrations. We're dealing with different ions. So typically they are numbered. So Ka1 is the K constant for the first hydrogen, and Ka2 is relative to the equilibrium of the second hydrogen. Okay, so you're going to see this in this example. So polyprotic just means more than 1 proton or more than 1 hydrogen ion that can ionize. So the ionizations happen in individual steps because each one is its own equilibrium. So here we have phosphoric acid as an example. So notice there are 3 hydrogens that it has the ability to ionize. So phosphoric acid is actually going to have 3 different equilibrium systems. We have H3PO4 becoming H2PO4 -1, and here's the Ka1 expression. So it's the products over reactants, and this is 1 constant. If we were to react out the next ion, so meaning now we want to see the second hydrogen leave, it's H2PO4 -1 plus water, right? So now we're going to lose 1 hydrogen. Only 1 hydrogen ever ionizes per equilibrium. So then we're left with HPO4 -2 and hydronium. So notice this is now called Ka2 because it's the second hydrogen that is leaving. So you have your products over reactants again, and notice the number is different. It's its own K value. And since we have 1 more hydrogen that we can lose, we can react this with water once again and have that last hydrogen go. Notice this is called Ka3 because it's the 3rd hydrogen to be leaving. So HPO4 -2 has become PO4 -3. So again, still products over reactants, and notice it's a different value. It's its own equilibrium. Okay, it's important to keep in mind as well that there's a trend happening here. Okay, so this weak acid, so the first equilibrium, the K value is much larger than the second K value. And the third equilibrium is actually much smaller than the second. So what's happening here is with each subsequent equilibrium for that weak acid, there is less and less product being produced. So what's happening is it's becoming weaker and weaker as it continues to ionize. Okay, all acids work this way that have more than 1 hydrogen. The first ionization is always the strongest, and it typically becomes weaker after that.